Today I'm going to talk about Tracee and real-time events processing in the security context. My name is Rafael Tinoco, and I'm an engineer at Aqua Security Open Source Group. I'll be doing this presentation together with Nadav, who is also an engineer at Aqua Security. We're both maintainers of the project, together with Yaniv, the project creator. The idea here is to have Nonas talk about how difficult tracing high amount of events from eBPF programs can be, when also taking care of portability and supportability and some of the blockers we faced and how we're trying to overcome them. So first I'm going to describe a little bit about the project for context. Tracee was born as a security forensics tool and evolved into a more complete solution for detecting behavior patterns based on written signatures that describe those patterns. We may see Tracee as two big parts: the eBPF kernel part and Userland event collectors and pipeline logic, and the rules or signatures logic, responsible for reading events out of the introspection tool and submitting detections based on described rules. We will be focusing in the first part only for this presentation. As you can see here in the simple diagram, Tracee eBPF is the most left part of the picture, collecting events from kernel probes and sharing them with Userland through libeBPF Go, a Golang library wrapping libeBPF. By using libeBPF Go, all the logic pulling the events file descriptor and calling a callback is done through one or multiple Golang channels, and the events are received in Userland through those channels. By the time the events arrive the Userland, a pipeline is started and is responsible for decoding the events. Depending on the event types, it has to know the amount of arguments being sent from kernel to Userland. The pipeline sometimes has to connect to external APIs to get information that will enrich the event's context. After processed, sorted, cached, enriched, and sometimes derived into other events, the event is sent to the second portion of the project, at the rightmost side of the picture, the detection mechanism, or what we call Tracee rules. Tracee rules will compare received events with signatures written in Golang, Rego, or GoCell, which is a feature being added now, and deliver detections in different formats and by different means. So this is an example on how to use Tracee. As you can see the command line here, we're basically executing Tracee, asking for JSON output as format. We're parsing argument flags so they are human readable, and we're detecting the syscall that generated an event together with the event. We're tracing the command ls, we're tracing the syscall openat, and we're filtering the openat syscall whenever the path name is etc wildcard. So now we execute the command and Tracee is executed. And we can simply execute ls and observe all the files that were opened into /etc. In this case, ld.so.cache, as the wildcard asked for. Now the second example shows a similar example, but now we're using a network event and we're filtering for the ping command. So executing the second example, we can ping a host and observe in JSON all the headers attributes, as shown here. Now the third example is a little bit more complex, as we're basically piping the output from the introspection tool to the input of the detection mechanism. And we're asking for all the events that this detection mechanism needs for the default signatures in place. So executing the third example, and we're using a Docker container to simulate behaviors that we need detected. So in here, we just simulated one type of the signature, and in the second example, another signature. As you can see, the signatures detect patterns based on what we've written in those signatures, right? So this example here is detecting that an executable was dropped during the runtime of, for example, a container. And we can also have other types of events like dynamic code loading or many other events that will be shown in this presentation. This other simple flow graph focuses in major logic of the pipeline, serving as a base for the next slides. From the top to the bottom, we will be focusing in the handle events portion of the diagram. All the perf buffer events from all the eBPF programs loaded and attached, depending on the requested event types, either by command line or through the signatures being used in Tracee rules, are sent to a single Golang channel through eBPF Go and decoded into an event type that will vary according to the events being submitted and provided arguments. After decoding part, multiple channels are concatenated into the pipeline logic that allows the events to sort events. Despite being submitted through single perf buffer, sometimes the same execution logic inside the kernel might have two probes and generate out-of-order events. It also allows to cache the events. I'll be talking a little bit more about caching events and why it is needed, despite perf buffer and Golang channel buffers. It allows us to process the events, to save internal information for subsequent events, or act to generate new events and save context for the future. Derive events. A single kernel event might generate one or multiple other userland originated events with data from that event or from the saved context from previous events. It allows us to parse the event data, parse arguments from bits and bytes into human readable arguments for the JSON output or the table output, for example. We will be focusing into this pipeline and problems in trying to cope with the throughput of events coming from the kernel. Whenever talking about event processing in Userland, we have to have in mind the following facts. Creating a portable eBPF application capable of running into many different released and long-term support kernels requires some creativity to the lack of eBPF functionalities, or sometimes verifier bugs in older kernels. Different eBPF program types have different overhead. More and more, the correct approach seems to be detecting the runtime environment and selecting the appropriate eBPF program containing better eBPF features, if that is allowed. And of course, relying on older ones, less capable and using less eBPF helpers and more complex programs whenever that is needed. We have to also have in mind that copying data over and over before processing is costly. Of course, the perf buffer might be replaced by ring buffers and avoid extra data copying, but also when doing high-level language in Userland, make sure that the events are not being copied over and over in the heap is also needed. This will save cycles for garbage collector and cause less latencies in the pipeline. eBPF programs are running in all CPUs. Your Userland tool is not. You have to understand the resource consumption thresholds the app will have available and plan accordingly. A big part of this discussion will be taken by Nadav when talking about filtering events. Nadav will also differentiate the runtime and frequency metrics of probes in the very next slide.
Okay, let's focus on a cause of eBPF overhead which we faced in Tracee. While eBPF brings many benefits as a safe method of writing kernel code, it's not without its risks in performance. As with most software, this overhead can be summed up intuitively by the formula of runtime times call frequency. This means that most performance bottlenecks will come from hot path hooks. We can measure these overheads quite simply with eBPF tool, as I will now show in a video. First, we enable with syscontrol kernel.bpf start enabled, run Tracee. Now we will print the program with eBPF tool prog show. I will show our trace point and show the important stats we measure. As you can see, we have runtime nanoseconds and run count, which is the runtime of the hooks overall in nanoseconds, and the count, which we can divide to get the average, as we do in this wrapper script. As you can see, with sysenter and sysexit, after optimizations and with some syscalls hooked, we get this average. Now that we've shown how we can measure eBPF programs overhead, let's talk about a use case we've had for this. Tracee can track all syscalls out of the box with hooks on sysenter and sysexit, and storing the syscall information in a map between the two. Some time ago, we also discovered that Tracee could cause latency issues for networking applications, and our first suspect was the kernel level code. Using this tool, we discovered how much runtime these hooks have taken. The simplest solution is obviously short-circuiting the logic if the syscall event isn't tracked. But Tracee uses syscall info in other security-related events and must keep the information even if you don't submit such events. As such, our fix took the following form. 1. We split the syscall tracking into 3 stages. First, detect the syscall. If 32-bit, convert to its 64-bit equivalent ID. Second, we gather all our necessary syscall data, ID and arguments, and store them in our tasks tracking map. Each task has a syscall running at a time, and we keep that syscall in a task tracing map. Finally, we submit an event for the syscall only if such an event was requested using the data collected in the previous stage. And we have to connect all the stages in the tail calls, otherwise instruction size limit may come into play in all the kernel. By fine-tuning our syscall collection stages, we were able to practically remedy our latency issues and found a potentially useful technique for solving other similar issues in the future. Now let's move to Rafael for the challenges of eBPF features in different kernel versions.
Some caveats when trying to take care of performance, but also worrying about eBPF portability. Introspection code does not have the full OS network context like other solutions, such as Kubernetes CNIs, for example. So knowing when an interface is attached or detached, or about network address translations happening in the net filter layer before arriving in the socket might be difficult. I'm going to talk a little bit about that later on. C-group eBPF programs helpers support in kernels below 5.6 is very lousy for introspection. Of course, the original idea for those eBPF programs was to mangle SKBs and do packet translations, socket lookups, and things like that. But missing generic tracing helpers, such as the simple ability of discovering the current task or current UID, makes correlating flows and tasks a bit difficult. The lack of more modern helpers to correlate flows, such as socket cookies or the local socket storage helpers, is also something bad. Then we have also the problem described earlier of missing eBPF functionality. Missing more performatic eBPF program types with better trampoline logic might make your program less fast. More and more the projects are probing features and having multiple eBPF programs for multiple kernel versions. A very good example that illustrates the performance penalty for mitigating older kernel versions might be this one. Instead of creating the event context that will be sent to Userland, inside the C-group ingress and egress eBPF programs, a kernel probe is set at the C-group program caller and its red probe. In this example, this kprobe and this kred probe can be thought as probe that will run right before a network packet is handled by ingress and egress BPF programs, and right after the same program runs. If the needed eBPF helpers were available inside the C-group eBPF program context, these two probes could be gone and all this work could be done directly inside the C-group program. But because they're not, all the data is calculated in a regular kprobe with all the helpers available and held in a BPF map, used as a scratch data until the head probe fires. This way, the C-group eBPF program will be as easy as querying a map and submitting the event to Userland, as you can see in the next slide.
Before we dive into the event pipeline internals, it is important to introduce the concept of the producer-consumer ratio. As written here in the definition, it is the ratio of maximum theoretical throughput between a producer and a consumer. That is, if a producer produces an X amount of data and the consumer can consume only Y amount of data and X is larger than Y, then you will have a bottleneck between the two. In the case of the eBPF perf buffer, that means lost events. And it's a critical problem in the security context because that means a detection could be lost. That is why, and we'll explore this later on, filtering is so important because it reduces the chance to reach our consumer's maximum capacity. And if our producer is also a consumer, it can also increase its maximum throughput capacity. Practically, we don't use this as a measurement, but rather as a reasoning tool. For decision making, we usually consult CPU flame graphs generated from pprof and correlate them with event throughput and the event loss rate, which we export through Prometheus. Now back to Rafael to start us on the pipeline.
In this diagram, the most important part to observe, as already stated before, is the fact that events are coming from multiple CPUs and sometimes at a very high frequency. If the perf events buffer map is not consumed quickly, it might be oversubscribed and event losses might happen. And that is for sure not good for a security detection tool. Let's assume for a second that your producer-consumer ratio is 1:1, and you're not losing events being produced by the kernel. Eventually, a CPU load burst happens, and because your consumer, the pattern detection, is dependent of the signature as evaluations, your pipeline gets stuck for a fraction of a second, but enough to cause event loss. This is where internal buffers and caches might help. By knowing eBPF perf buffer, one could think that simply raising the perf buffer amount of pages could mitigate the issue. Unfortunately, that's not easy, as long-living servers might not have available contiguous pages to satisfy that need during the program's startup. Since Tracee uses eBPF Go, another thought could be that simply raising the goline channel buffer could help in that situation, turning the channel asynchronous and letting the runtime to take care of the queued events. Unfortunately, that is also not true, as the runtime overhead to manage so many queued events will step into performance and cause pipeline latencies. The best approach was to cache events in heap, as fast as it could be cached, and have multiple routines dequeuing the events as the consumer allowed. The size of the cache is also configurable, and it won't allow the disparity in between producer-consumer ratio to be very long. So it allows load bursts, but of course not infinite disparity in between the producer and consumer. So with that in mind, Nadav will be talking about how to reduce the throughput of events from the kernel to userland using filters.
Now let's talk about filtering in the pipeline. Filtering is a critical part of Tracee for reducing event loss, and it's currently a domain where we are investing development time, as it can heavily reduce event loss. In Tracee eBPF, there are currently two places where we filter: inside the kernel, where we compare our events to a global context, and I will show just in a minute what the context is, and in Userland, where we do per-event filtering, which we can allow to be more complex due to being in Userland and not being limited by eBPF capabilities. While doing all of the filtering work in the kernel would be ideal, it is much harder to implement and support the variety of features we can have for Userland filtering. First of all, this is the event structure we have. Most of the fields here are what we call the event context, and at the bottom we have the event arguments, which are specific arguments that we have per event and include unique values. For example, file descriptors in opening file events. Filtering in the decoding stage allows us to skip a lot of processing later down the line, giving the eBPF Go polling more chances to extract events from the perf buffer, thus reducing the chance for lost events. In addition, we include a per-event context filter at this stage, also using Userland filters, which works just before the argument filters, as it's usually quicker and can help us avoid the argument filtering. We plan to use all of this in the future to inform Tracee through its behavioral signatures in Tracee roles what filtering it should use. So let's talk about what our Userland filtering optimally needs to look like. First, it must not impact the producer-consumer ratio negatively on the consumer side. Second, argument filters need to support all available argument types. Currently, we do this for string casting and using string filtering, but we are currently looking at using Go generics from 1.18 as a solution. Finally, string filtering needs to take advantage of being in Userland, and as such, we include prefix, suffix, and contained matching filters, and we can include infinitely as many as we want. Let's take a look at an example of how we optimized such filtering in Userland. On the right side is our naive implementation of string filtering. However, since we know our filters before runtime, we can do better than this. This one takes O of n, where n is the amount of filters we have. On the bottom right is our new string filter implementation. Notice that it sequentially checks between prefixes, suffixes, and contains. However, by using a technique of combining a dictionary of our prefixes and counting their unique lengths, we can do a much more efficient match between a value and the mass of prefixes or suffixes, since that is simply the reverse. This would take O of n, where n is the amount of unique prefix lengths we have, which, let's say if we have 50 filters but 5 unique lengths, it's much quicker. It's reasonable to guess that a similar optimization can be done for the contained filters. However, we haven't done research into it yet. So let's recap the current limitations we have and potential improvements we can do. First, Tracee currently only supports one global filtering scope, which makes it difficult to have conflicting and parallel filters. However, work is currently being done to add that as a feature. And as said previously, our argument filtering capability is currently limited to string values and typecasting, and so we depend on that, but we're aiming to fix that soon. 3, filtering happens before event derivations. Finally, filtering in Userland is at the end of the day less performant than working inside the kernel due to stopping submissions from the get-go. It's possible that we could maybe move some of the string filtering capabilities we have to the kernel in the future, maybe only for some specialized events, and maybe from newer kernels and onward. Now that we've tackled how we reduce processing work, let's talk about what we actually process in our pipeline. We have currently 4 different categories of processing we do for events. 1, logic hooks done after filtering, and this is mainly done to change states and caches the Tracee holds. 2, event enrichment, querying more fields into our event context or arguments, and the main example of that is container enrichment, which we will discuss next. 3, event derivation. That is logic that correlates some event, generally generated in kernel, to a new userland generated event. For example, a cgroup make their event, basically a cgroup being created, can be correlated to a container being created, which is a separate event. Finally, we have argument parsing, which is the last hook point for logic in the pipeline, and this is done in order to make arguments user-readable. For example, some of our arguments come in the form of numbers, like ptrace requests and file descriptors, so you can translate them to a form readable by users. This is technically an optional stage, but writing Golang rules usually requires this stage. Now let's talk about the feature of container enrichment. As mentioned before, container enrichment enriches the event context with information related to a running container where it happened, namely its container ID, image, and name. In addition, we support Kubernetes awareness and also include pod name, UID, and namespace if it is relevant. We are currently implementing this feature at Userland by parsing cgroup paths to find the container ID and runtime and querying the relevant container runtime interface. And I've listed the challenges related to that. But I'd like to discuss the last challenge in particular. That is requesting info from container runtime is synchronous, but our pipeline cannot be synchronous. Of course, some of you may know that container runtimes also export an event interface, but that interface alone is sadly not sufficient for us, since it doesn't include the container's Kubernetes data injected into annotations by kubelet. Our architecture for enrichment had to include a whole pipeline stage dedicated to querying the runtimes and enriching events. The requirement was that this stage will 1, not block the pipeline under stress, and 2, enrich only the necessary events. Let's now look at the design. We have one mutex which is shared across 3 Go routines. We opted for one big lock because fine-tuning our read-write lock was causing deadlock bugs, opting for a simpler design to solve those. We have 3 Go routines, as can be seen here, which do the following. 1 ranges over events. Check if they need enrichment or signals and enrichment cleanup. If it does, send it to its appropriate queue, and invoke an enrichment request if needed. Finally, send an enrichment readiness check. We have another Go routine, which ranges over these enrichment checks. If a cgroup enrichment is ready, pop an event from its relevant queue and send it out to the pipeline. Otherwise, we reschedule the check by sending it back to the same channel. And 3, we range over cgroup cleanup checks. This checks if the relevant cgroup queue is clean, its length is 0, and if it is, we clean up all relevant resources. Otherwise, we reschedule the cleanup. This currently works well under a regular workload and can handle the stress of many new containers without blocking the pipeline. However, in cases where the container runtime interface is overworked, it will skip enrichment, but it will not block the pipeline. Now, let's talk about a potential alternative implementation for this that may be more performant and may be researched in the future. We can use eBPF view probes to hook the runtime daemons container creation routines, and we can extract container creation data at the heart of operations. However, there are some issues with Golang and eBPF view red probes. It can cause runtime crashes, and there's a good article about it which I've linked below, but it's certainly an avenue to explore. Now, let's move back to Rafael for more in-depth discussion of event derivation and how logic there could hinder the pipeline.
Continuing an example of possible delays in the pipeline, we have one of the supported features, tracing symbols being loaded by shared objects. With this feature, it is possible to trace specific symbols being loaded and from which libraries they should or shouldn't be loaded from. In this example here, we're tracing all the fopen symbols coming from any shared object that is not libc. This allows us to trace all the preloads that would cause the symbol to be called from other libraries than the real ones. A security memory map file kernel event derives a symbol loaded userland event, if that is the case. There are many problems in trying to do that. The memory mapped file paths coming from the kernel events might be part of a bind mount root tree from a container. To solve that, there is a path resolver object that will always convert file path names to absolute path names. The second problem is related to asynchronous event processing. By the time that event arrives at this moment in the pipeline, it might be that the task that generated this event has already exited, for example. make it hard to find the root file system and read the shared object that was memory mapped in that task's virtual memory address space. We use sometimes techniques like trying to find other tasks in the same namespace, considering a map of tasks and namespace is kept from in memory from the beginning of the pipeline. There is also sometimes the need for saving events for further processing. Instead of processing the events right away, to save them to be used in the near future when new events arrive. This is the example of the hook detections feature. If we think of a kernel module being loaded, the event is submitted to Userland. Userland now needs to compare the current symbol addresses, like kernel system call table indexes, or sec, net operations, or file operations pointers, in order to understand if that kernel module has hooked into something important to hijack that function. The best way to kick a kernel eBPF program is through a new probe hooked to a Userland function. With that, we simply call an internal function of the program, passing arguments, and the uprobe hook runs. The uprobe hook sends the symbol addresses to Userland, and with the saved context from the original kernel module event, Tracee detects if that event caused a hook or not. Obviously, this type of event is not as often as others, but it explains the need for saving event contexts from time to time. Another way of delaying the pipeline is network protocol handling. Obviously, the idea for eBPF network programs is usually to mangle packets, redistribute, or balance them as needed. But for tracing purposes, we would like to submit information about those packets, sometimes even the full packet payload, to Userland. From the left to the right, we will observe how this is done. eBPF programs correlate network sockets and the file descriptors that opened their inodes. With that, it is possible to trace the flows in ingress and egress after low-level network code has been executed, and observe packets much closer to the proxies than other eBPF solutions, acting much earlier in the stack, like CNIs using XTP or TCP or TC eBPF programs. One approach we already use as well, but proved to be error-prone for runtime, as interfaces would appear and vanish, and not having to bind programs to interface was a much cleaner solution. Through cgroup ingress egress programs and perf buffers, the packets are submitted to Userland in raw format, with all headers, and sometimes the full packets are sent, to be processed by derived events. There are two eBPF event channels. One is for events and patterns detections based on header information, and the other is for capturing the full packets if capturing feature is set. The network events are derived into specific network typed events to be sent down the pipe to the detection mechanism, which is what you can see in the rightmost part of the picture. Some full protocol events might even be derived into more simple ones, as the DNS event, for example. The full DNS responses might be hard to consume, so each response might be broken into more simple DNS query reply events. This is just an example of related code. As you can see, each network packet has raw event with the entire network header as the payload argument. It then derives IPv4 and IPv6 events, if that is the case. On the right, the code deriving the payload, parsing the packet data using GoPacket library.
Finally, let's talk about the last stage in the pipeline, which is encoding to bytes, which can be a significant bottleneck for performance in the pipeline. In Tracee, we send events in a byte stream through a Unix named pipe between Tracee eBPF and the rules engine Tracee rules. Even encoding alone, as can be seen here, can take a significant chunk of processing time. And if done also in decoding in Tracee rules, that can really harm the producer-consumer ratio, which will also harm the producer-consumer ratio between Tracee eBPF and the perf buffer, causing event loss. Currently, we use GOB for encoding in the full Tracee experience, but we are looking at some potential better alternatives, so let's talk about those and the requirements. So we have two requirements that we have for encoding. One is that it must support maps, slices, and complex structs that include those two. And two, that it guarantees the type safety of values stored in the empty interface type. GOB guarantees both, but it is not very optimal in performance, as has been seen. And out of the box, most encodings don't keep the Golang type info across boundaries without modification, and may not support maps, slices, and complex structs. The current alternatives we are exploring are one protocol buffers, which we also use currently in GoCell. That is the reason it is the ideal candidate currently. However, we need to hardcode our argument types. The generic solutions discussed before can be used to solve that. 2, message pack. This almost works out of the box in code generation, but it can lose type info. For example, an int32 can turn into an int8 if it's stored in the interface type. With code generation, you can step in as the developer, but that is not ideal. 3, flat buffers. This is a very uniquely interesting solution since it is very fast. However, it doesn't support the map types in Golang. Finally, you can roll your own, but for obvious reasons, that is very error prone. So currently, protocol buffer seems to be the direction to go. Now, let's join Rafael for conclusions.
With all that has been said, these are the conclusions. To use different eBPF programs or set of programs for each feature you would like to have, depending on the kernel versions you would like to support. To select carefully what to probe and to return from the hooks as fast as you can. To have multiple parallel in-kernel filters. Userland pre-processing, context saving and filtering will always have its place. Events consumer cannot block the pipeline no matter what, or else event loss will happen. The types should be kept over the pipeline to all of the consumers, so the decoding process doesn't step into performance. With that, I would like to thank you and invite you to reach us if you have any questions, doubts, or suggestions for the project. Thank you.
Cool. Okay, so I think Raphael was also on the Discord channel. If you think of any questions that you want to ask them, they were there. You can message them. Thank you again to